Okay, so what we're going to do is we're going to calculate the rate of decomposition of carbon disulfide liquid into its elements. Okay, so how would I go about doing that? How would I calculate the rate law of that? So what would be the generic rate law? Okay, so we have K times the concentration of C S2 to the X. Okay. So how would I go about doing this? So we're gonna have to find the order. So how would I go about solving for the order? That's true. What else is also we're gonna need to find? So we're gonna be looking for the order, which is the X. We also need to find K. So these are our knowns here. So how would I go about using the data that's provided? What was that? So we're provided the rates, right? And we have all of the rates for each of the different experiments, right? So we're going to use the different experiments to sit there and calculate the order. Okay, so if I'm going to do that, then I'm going to go, let's see, let's start off with the very first one. Okay, so then we know that this rate, 2.7.70 times 10 to the -7 is going to equal K, the concentration, which is 0.11. Oops, sorry, 0.10, sorry. And then to the X power. Now we have two unknowns. So we need to have two equations to solve for those two unknowns, right? So then we need to set up another equation. So we can use that second one. So we can use 2.20 times 10 to the -7 is equal to K 0.0800 to the X power. Okay. So then we can solve for either the K or the X. So let's go ahead and solve for the K. So we'll go for the first equation, then we'll substitute that in for the second equation. So then we'll have K. We'll say this is equation A. Make it easier. So we're going to solve equation A for K. So we have K is going to be equal to 2.70 times 10 to the negative 7. Oops. Sorry. Do you guys feel like you're in a math class yet? All over 0.100 to the x power. And then we're going to substitute that into our second equation, equation B. So then we'll get 2.20 times 10 to the minus 7 equals 2.70 times 10 to the minus 7 over 0.100 to the x power. Okay. And that is going to be times 0.00.080 Okay. Okay. So then we solve. Try to solve for x, right? So then we'll get 2.20 times 10 to the minus 7 divided by 2.70 times 10 to the minus 7 is equal to, so we have 0.0800 to the x power divided by 0.100 to the x power. So we know that since we have this number to the exponent, what we can do is we could take the log so that we would end up solving for x, right? Or we can bring this out, and so we can end up having this number, which is, hold on, do the math real quick so I don't have to carry around so much weight. 0.0800 divided by 0.1. So then that's 0.8 to the x power is going to equal 10 to the minus 7 cancels out, so we get 0.22 divided by 2.7. So then that's 0.8, and that would be 366, so that's 815. Okay, you guys are agree with me there? Do you mind if I erase this stuff up top so that I can, okay, although we're going to need it a little bit later. Let's see, running out of room here. Okay. Okay. So then, if we take the log of both sides, or the natural log of both sides, where's my, so we get ln, oops, ln 0.8 to the x power. So that's the same thing as saying x ln 0.8. And what I do to one side, I have to do to the other side. It's going to be equal to ln 0.815. Oops. Yep, so what you do to one side, you have to do to the other side, right? Rule that we know is chemistry and math and everything, so. Okay, so going to get x is going to equal ln 0.815 divided by ln 0.8. Okay, what did you guys get? Okay. We get x equals, you said, 0.917. Okay. Questions, concerns, Kool-Aid? Okay. And then we could plug that in and we can solve for k. Right. So if we plug that into the first equation and solve for k, so then we'll get, let's see, use my eraser. Do you guys mind if I erase this part down here? And then we'll erase this one since we're going to use the first equation. Third grade handwriting. So we have 2.70 times 10 to the minus 7 equals k 0.100 to the 0.917. Okay, so we solve for k, we get k equals 2.70 times 10 to the minus 7 over 0.100 0.917. Okay, e -7 divided by 0.1. So we get k is equal to 2.70 2.23 times 10 to the -6. Okay, then our equation is going to be rate is going to be equal to 2.23 times 10 to the -6. CS2, concentration of CS2 to the 0, to the 0.917 power. Okay, so that's going to be my final answer. Questions? Piece of cake? Do you guys see how to use the? Yeah, I need to fix your homeworks too, because I think they're a little off. Are you guys doing kinetics right now? Chem 101? Or did it open up? It hasn't opened up? Okay, so let me see what's wrong with it. So I'm on a roll with Chem 101 right now. Actually, this will be the second time I have to fix something. Yeah, so I'll fix that so you guys will have access to it. Let me put a note on my to-do list. Cool. What was that? I don't want you guys to fall behind. Okay. Oh, question. I have announcements that I'm supposed to make. Okay, so unfortunately, we won't be able to have the physics class available for this semester. However, we are planning to have it for the fall. So we'll have 4A and 2A offered in the fall semester of this coming year. I know that some of you guys are planning on leaving or transferring here soon. So I guess most of you guys are, but you guys all need OChem anyway. So you can stay around for physics and OChem. It'll be a party. And then hopefully by that time, we'll actually have all the supplies that we need to complete a lab. That's a whole another story today. So. No, so what it's gonna be for the fall. We're gonna do it different than Lemoore. So Lemoore has 4A in the spring. We're gonna have 4A in the fall. So we're gonna offer 4A in the fall and 2A in the fall. And then it'll be 4B and then 2B. Because we have a physics that's an adjunct instructor, so she'll be able to teach physics courses. Barely. So what was that? Yes, we're also going to get the 4C activated, and then so that will be if we can get her hired on, so she can teach the 4C series as well. Yeah, but we have to show that there's a demand before we actually try to get her officially hired on. So. Don't cry, it's okay. Okay, so so it's a work in progress, but definitely it looks like it's going to happen in the fall. And then if you have people that are interested in elementary school teaching AST, so there's a class that's physical science 2 that's required. We'll be offering that in the fall. So, and that one's already set up. Definitely. So, Okay. Well, you can still take it, even if you do get accepted, take a class here, you know, and the teacher that is going to be teaching it, she's really good. She, at least from what I saw, really, really good. And then two of the students had her she's an adjunct at another one of the community colleges, and they had her there, and they're like, she is really good. So, okay, so let's continue about the rate constant. So the rate constant is going to be, it's not going to be dependent on concentration, but it is going to be dependent on temperature. Okay, and that's going to kind of come into play later on. So when we start adjusting the temperature for reactions, we speed up our reactions, then we're going to have to reevaluate and recalculate the rate constant. In most cases, the rate constant has to be determined experimentally. So your initial rate constant that you had at a specific temperature has to be determined experimentally. Now, if you have your rate constants and you have the amount of energy, or you calculated the amount of energy, there's a threshold energy that needs to be pushed over, and all of that is, or we call it the activation energy. You can use the activation energy and then the temperature to calculate what the rate constant would be. And I'll show you guys that information here in a minute, okay? So as you guys can see, from this data, the determination of your rate constant and everything is going to have to be done experimentally, and then you use the data that you've collected to sit there and calculate it. The order of the reaction has to be determined experimentally as well too. Okay, so those are the two things that are definitely going to have to be determined experimentally. Okay, so so you can't rely on stoichiometry, right? Or a balanced chemical equation to sit there and determine the rate constant or the order. That's right. You got to do the work. There's no quick and easy way. What was that? Yeah, because every reaction is going to be slightly different. It's not going to be based on the quantity that's there. I mean, it affects it. How much is there is going to affect it, obviously, because its concentration is a factor in it. But to determine how fast a reaction is going to happen, it has to be done experimentally. Right? Does that make sense? Yeah. Now, I mean, once you do it experimentally, right, and you've done it enough times, then you can say, okay, yeah, this is definitely the rate constant. There's not like we don't have a tabloid of all of the rate constants, right? And so, and that's only done, like I said, experimentally, experiment from experiment. And then again, that also has to be done at the same temperature. Okay, so reaction orders. I'm sorry, the order of the reaction is usually a positive number. You can, and it has happened. I took a course in chemical engineering, and we were calculating the rate constant, and it was actually a negative value for the order, which is totally insane. And it was real because we did the experiment like 15 times. I thought it was bullshit, right? And I'm like, there's no way. You can get situations that happens, but usually it's going to be a positive order. It's going to either be 0, 1, 2, 3. You can have fractions and you can have negative numbers, but it's very rare. Okay. Let's see. So a lot of times we're going to deal with reactions that are going to involve more than one reaction. So those guys are going to call the bimolecule or bimolecular reactions. Okay. So which basically means more than one. So in that case, again, the rate constant is going to be written like this. And then there's going to be what we call three orders that are going to be talked about, right? So the first order is going to be for the first reactant. The second order is going to be, not second order, we're going to find the order for the first reaction. We're going to find the order for the second reaction. And then we're going to find the order for the total reaction, which is just the sum of the first and the second, the order of the first and second. Okay? You can use X and Y. It's fine. Either one is fine. This is the one that they use. Okay, so this is just basically showing you ozone. Like, so if we're looking at like the decomposition of ozone based upon the atmospheric reaction. So we could sit there and establish a rate constant of how much ozone will be depleted over a certain amount of time, right? Or we could find, as I said, the rate of ozone depletion. Okay, so okay. So the next thing that we're going to talk about is let's see. Okay, so as we shown you earlier in the examples, so one way that you're going to determine the rate law of the reaction, the rate law of the reaction is by measuring the initial rates. And so that was kind of what we showed you with the decomposition of carbon disulfide. Now, if you guys remember, there's a picture that we showed earlier. So long as we're in that same region where that reaction is being maintained consistently, we'll be able to sit there and establish the rate constant there. But like in the case of, so we have a slope that's happening here, and then we have another slope that's happening as the reaction goes further. So as time goes on further, that reaction is going to change. And because of that, that range of that reaction is going to be kind of dependent. So we could end up getting situations where we have a rate under this circumstance and then another rate under another circumstance. Okay. Or another length of time. So. Okay. Questions, concerns, cash, Kool-Aid. Now, kinetics is like heavy math. If you guys haven't noticed, it's very, very heavy math. So we're going to add a couple more things to it. And then, and so the next thing that we're going to be talking about is the integrated rate law. How many of you guys have taken calculus? Okay, and you guys are familiar with the integral? Okay. So you guys are going to be introduced to, so almost everybody here is taking calculus, so we're kind of getting that sense you guys will have an understanding. So the integrated rate law is basically taking the integral of our rate itself, because if you think about the rate, it's going to be written down as n the change in concentration, say of A, over the change in time. Have it. Okay, so normally we've been using delta. We can also use that d, sort of like the derivative, right? You guys remember derivatives, right? And then, so we could also use that in terms of the integral. Okay, so then we could separate that derivative and then solve for the integral. And so that's going to be equal to our K, the concentration of A. And let's assume for simplicity cases, A is to the first power, right? So then what we'll end up doing is getting dA, concentration, is going to be and again A over dt. And then you just take the integral of both sides, and then so you will get the concentration of A from a given point to another given point, initial to final, is going to be equal to the concentration of A to dt. Okay, so then we'll integrate both of those sides, and we'll come up with a nice, beautiful equation. Okay, so let me show you first order reaction, first order integral reaction. So this would be the first order integral reaction. So that's basically where we actually done that integral. So if we took the integral of A, of that concentration, so you're making the assumption that we had this rate here, and I showed you that dt. So this would, if you solve that integral, this is what you'll end up. Does that make sense? Because it'll be, what was that? Oh, you were thinking about having numbers in there? Yeah. So in other words, you're saying that if we take that integral, let me go back to that one. I got ahead of myself. So if we take the integral of both sides, right? So when you take the integral of this, so then you'll end up with this guy is going to be ln. So you're taking it from t, 0 to t. So from t to 0, okay, or 0 to t, okay? So this guy is going to be ln A. And then we're taking it from that limit from 0 to whatever time that is. So that's how we end up with ln. This is A naught. ln t. And then that's going to be equal to, because this is just going to be kt. Because, oh, I guess let me do one more thing. We bring this guy over to the other side, right? So you get, I'm rusty here. Bear with me. So t A dA is equal to K dt. So this is kind of like K is a constant, so it's being multiplied by 1. The integral of 1 is just going to be x, or in this case, t. So this is how we end up with this guy here. Oops, sorry. I'm pointing to something that you guys can't see yet, right? This guy here. So that's how we end up with this guy here. Okay, so it's just basically the integral. You don't need to know how to do integrals to sit there and calculate it. All you need to know is that first order reactions, this is the equation that you're going to be using. Okay, but if you know how to do the integrals, it helps. Okay, so that basically means that at time, the initial time, this is going to be the concentration that we're starting off with. And then whatever time lapse at time t, 5 minutes, 10 minutes, whatever it is, this would be that concentration. And then that's going to be equal to K times time. Okay. Piece of cake. Okay. So now, a lot of times we're going to have to rely on it being, we're going to have to rely on it, on the data collected to calculate the variables that are going to be missing. Okay, so what we're going to end up doing is that we're going to change the first order reaction, because if we take a look at this reaction, we can make modifications based upon the rules of logarithmic or logs. Okay, so the natural log, if you have the natural log of A naught over A, you can actually break this down to be ln A naught minus ln A T equal KT. Okay, so if we adjust this, so we could have ln A T equal minus KT plus ln A naught. Does this look like an equation that you guys are familiar with, where you have T acting as one of the variables, and then this ln A acting as the other? No? That's right. So if we use y as a substitution for this, equal to where k represents the slope, m x, and then ln. Okay, so this is just the equation for a line, right? So that's the beauty about a first order equation. It's that it's like the equation for a line. The only thing now you're using just ln. You just got to remember that it's ln, not y. Okay. And I like giving you, because I could just give you the equations and you guys memorize it, but I like showing you the math so you guys can see it and you can, oh yeah, relate. So, okay. Questions? No questions? You guys got it? Piece of cake? Okay, so we can actually do this. We can use, instead of concentrations, we can use partial pressures, right? If we're using gases. So this will work the same way with partial pressures rather than using, because we know that pressure is directly proportional to number of moles, right? Okay, so we can also use number of moles. We can also use number of molecules. So this equation we can actually get away with using just about anything, right? So we can use moles, number of molecules, we can use partial pressures. And we can also get away with using it for mass. Okay, so if we graph it, it's going to look something like this, right? A line. Okay, so that's what a first order reaction is going to look like. And again, you got to remember that we're plotting the natural log of the concentration over time. Okay. And the other thing is that you guys are going to have to get re-familiar with Excel. So I'm going to have you guys bring your laptops for our next lecture, right? And we'll be talking about it a little bit more. Okay. How are your brains doing so far? Pretty good? Okay, good. See if we can move on. Oh, yeah. Oh, yeah. Oh, yeah. This semester is going to be rough in terms of the math. Okay. Okay, so the other thing is I'm going to show you some examples here in a second. Okay, so often what you're going to end up having to do is plot the data that you're getting. And the reason I'm just showing you the examples rather than us going through the process, because you guys don't have a laptop, and I didn't tell you to bring your laptops. So although we could sit there and bring them, but I think we'll just wait, have you guys do it on Monday. Yeah, because we're going to shortcut it short, because I need to get out a little bit early today, because I have a program review to try to get written tonight and a budget. So they're trying to get budget requests to get written tonight. So do tomorrow. So I feel like I'm in school again. Yeah. And then I also have to order a shitload of stuff for OChem, because we obviously don't have a lot of stuff. We couldn't do an experiment today because of it. They keep postponing their experiments. Anyway, okay, so the next thing I wanted to talk about was half-lives. Okay, so you guys heard of half-lives of reaction? A lot of times when we talk about half-lives, we're talking about decay of a chemical compound or anything like that. Now, again, this is also based upon a first order reaction. In this case, you're assuming that first off, we have the first order of reaction, right? So the half-life of a reaction can just be broken down to T1/2 is equal to ln2 divided by K, right? Because we're saying that T is going to be equal 1/2 the initial concentration. That would be the half-life. Okay. It's just half the life, yeah. And the funny thing is that it's used in every field. Like, so if you look at toxology, you use half-life. If you look at, let's say, enzyme decay, half-life, right? And so you're going to be using radioactivity, the half-life, right? So, and it literally just means half the time, right? That you get half the amount, or I should say the time that you get half the amount that you want. So, okay, just like half the time. So that T, that time that it takes, is going to be equal to ln2 divided by K. Okay, where K again is representing the rate constant. Okay, so in that concentration, we know that the half-life is not dependent on the concentration. It is dependent on, because you already said you're getting half the initial concentration you're starting. Okay. Questions? Concerns? Catch? Okay. So this is just showing you, okay, so we have this reaction of decay of hydrogen peroxide at 40 degrees. And the color, the brighter it is, the more concentrated the peroxide is, the less the color it is, the lower the concentration. And so this here is just showing you the decay over time. And so this is an example where we could actually use the information to calculate our K value, right? And then we could use it to sit there and calculate the time that we have our half-life. Yes, sir. Yes, you can. And you can tell the guys next door that they can also leave early as well too. Yeah, yeah, they're going to do their lab, but I think I can handle it. Yeah, did you guys not finish? No. At the top? And you have it at the temperature is high enough this time? Okay. And what about theirs? Is it the same problem? Okay, so I'll take a look here. Okay. Okay, so a second order reaction, if you go through and do exactly the same concept. And so here we're saying that we are starting off with the rate constant is going to be equal to K, the concentration squared. So if you take the integral of this, then the second order reaction is going to look, it's going to look like this. So you're going to end up with 1 over the concentration of T is equal to KT plus 1 over the concentration of A naught. Oh, that's right. You just zoned out on me, huh? So it's just going to be 1 divided by the concentration of A to the T times T. Yep. Is going to equal to KT plus 1 over the initial concentration. Well, in a sense, this is a second reaction. So you're starting off here, right? So again, what we're doing is taking that dA over dt equal to K A squared. Okay. Now we're going dA. That's why I screwed up. Over A squared is equal to K dt. You take the integral of this, and we take the integral of this. So then you're going to end up with, and this goes from 0 to T. Okay. So then you're going to end up with 1 over the concentration of A from 0 to T. And if I remember, it should be -1 equals KT. You guys remember that from, okay. So again, you don't need to know that. What you need to know is this, but that's how you get there. That's where it starts from. That's right. Yeah. And so really there's a lot of calculus in chemistry, but for this class, we assume that most students haven't had calculus, or they're kind of taking calculus simultaneously, but they're not familiar with it yet. So. What's that? If you're planning to get your degree in chemistry, you definitely want to make sure you have the complete series. Yeah. Yeah. Well, no, actually, if you go to a 4-year school, if you're planning to go to a 4-year school, they're going to make you take 1 semester of calc. Yeah. That's BS. Yeah. So you have to take at least 1 semester of calc if you're going to go to if you're planning to get your BS in biology. Although I think you may be able to get a BA without taking. Yeah, you may be able to. But uh-huh. Uh-huh. Okay. Okay. Yeah, but usually they require 1 year. Yeah, because some parts of physiology, that aspect of it actually is based upon the interval. So even though we don't teach that aspect of it, which we should, but but we don't have many students that take that 1 year of calc. So okay. Okay, so that's what we're going to get for a second order reaction. And then I'm going to show you guys how to use all of these reactions on our next, because I'm going to have a little examples. The examples are going to take a while. And then I'm going to see if I can get a little pad to write on. It's crazy stuff. And you think my handwriting, my second grade handwriting is bad now. After that, my hand starts to cramp and everything. So, and then plus, like I said, there are going to be parts of it we're going to show you how to do these calculations with the computer. Saves you so much time. Okay. So the next one is a zero order reaction. A zero order reaction is really easy. So then you're just basically saying that the rate is equal to the initial concentration times K, right? And that's all it's going to be equal to. So then if you take the integral of that, you're going to end up with the concentration at a given time is going to be equal to minus K T plus the initial concentration. And so in this case, if for a zero reaction, the half-life is always going to be equal to the initial concentration divided by 2K. Okay. Questions? No questions. Good. Okay. So let's go ahead. We'll stop here and we'll pick up on collision theory on, what is today? Today's Wednesday, next Monday, right? Next Monday. So, and then what we'll do, we'll finish this pretty much in the next chapter. On Monday, what we'll do, we'll spend a little more time on lecture.